Well, greetings, mathletes, and welcome back. Um, so we have a couple of things to cover today. One is addition and subtraction of polynomials, and the other is multiplication of polynomials. Now, addition and subtraction is one of those things where we've actually been doing this, but we haven't given it a name, right? So really all we're going to do is just review what we've been doing, and then call it what it is now. Then when it comes to multiplication, it's going to turn out you actually have all the skills required for multiplying two polynomials already. It's a matter of taking those skills and putting them together correctly. So as long as we can do those things, we should be in good shape as far as this particular lesson goes. So without any further ado, let's go ahead and get started here. Okay, so let's say we have a couple of polynomials here. So I'm going to pick a couple of my favorite polynomials. We have, let's see, I got everything pen turned on. Oh, let's try this one more time. This time we'll turn that down a little bit. There, oh, too high. There we go. Back to 2 pixels. Okay, let's try it again. Now we'll try with some of my favorite polynomials. Are you kidding me? It just went back. Why did it go back? Sorry, technical difficulties. Seriously? Okay, so let's try this again. X squared minus 5x plus 2. So let's say that's one polynomial. Sorry about that little delay there. And let's say I want to add it to, oh geez, to this other polynomial. Right? So let's say this is what we're adding. Okay, so we have two polynomials here. One of the things that you'll notice is that in this particular case, these parentheses aren't really required to do the arithmetic here. The only reason the parentheses are there is to show you what the two polynomials you're adding actually are so that you can distinguish the two of them. Once you've distinguished them, if you're just adding them together, you can forget about the parentheses and look at the problem this way. And if you look at the problem that way, your gut instinct is probably telling you to collect like terms. And that's exactly what you do. You just find all the x squareds and put them together. So I have 1 here and 3 more over here. So altogether that makes 4x squareds. And then for the x's, in fact, I'm going to do this. I'm going to cross these off as I use them. So I have x's here now, and there's no other x's. So he's got no friends, so he's just going to sit exactly how he is. And then I have more like terms here, 2 and 10, and I add those together. So it really is just collecting like terms, right? That's the biggest issue that you're going to have with this is identifying. And it is something we've been doing, right? When we're solving equations and we distribute and collect like terms, we're actually adding polynomials together. So we've been doing this actually since the beginning of the semester. We just haven't called it that. Okay, so let's go ahead and take a look at another one here. Okay, now subtraction's slightly different, but it really ends up being the same thing ultimately. Now let's try this again. So let's say I have 2x minus 1, and I want to subtract from that 3x squared plus 5x minus 2. Okay, now here's the big difference, is that you have this subtraction sign, and it really functions as a -1 out in front here. So when you do subtraction, the thing you have to do first is distribute the negative to every term. Right? That's the big difference between addition and subtraction, is that subtraction requires this distribution. And so if I distribute that, the first part stays the same. And also, once I distribute this, I don't have to worry about the parentheses anymore. So that makes it minus 3x squared minus 5x and plus 2. The biggest mistake that's made with these types of problems is changing the sign of the first term and then forgetting about these last two. You have to distribute it all the way across. Once you do that, you can just start taking the terms in order. I like to start with the highest exponent. That's the particular order I'm talking about. So I'm going to start with the highest exponent and work my way to the lowest exponent. So negative 3x squared has no friends. So he's done now. And then the next thing down is x's. So I have 2x here minus 5x. So I have this and this. That gives me minus 3x. So I've used these now. And now minus 1 plus 2 is plus 1. And so we've just added these two polynomials together without too much issue. Okay, now the negative thing causes problems. That's usually the biggest problem. But then the other thing, sometimes when there's more than one variable in these polynomials, it gets a little bit confusing to look at. So I want to take a look at one of those, just so we understand what to look at and what to look for. So let's say I have negative 5a squared b to the third minus 2a to the third b squared plus a squared b squared, and I want to add that to 3a cubed b squared minus 2ab. Right? So there's a lot of a's and b's here. The thing that you want to remember is that like terms have exactly the same variable part. That's what you're going to be looking at. So all the same variables are there, and each variable has the same exponent as its corresponding part. So when you're identifying these as like terms, well, first of all, let me go ahead and just rewrite this now that I'm thinking about it. I'm going to rewrite it without parentheses, and then we're going to look at it one term at a time. So we have minus 5a squared b cubed minus 2a cubed b squared plus a squared b squared plus 3a cubed b squared minus 2ab. Okay, so what we're going to do is we're just going to go through this one term at a time until we've exhausted all of the terms. So I'm going to start here with this guy, minus 5a squared b cubed. So what I'm looking for is another a squared b cubed. I got an a squared, but b's not cubed. Okay, that's an a cubed, doesn't work, and that one's not squared. So this guy's by himself, right? There's no other part that has the same variables, and each variable has exactly the same exponents as this. So you're looking for not just the a and the b, but the a has to be squared and the b must be cubed as well. Okay, so we've used the first term. So let's turn to the second term now. So we're looking for an a cubed b squared. Hey, I got another one over here. Okay, so if I add those together, I have 3 of these and I'm taking 2 away. So I have plus 1a cubed b squared. And I don't need to write the 1. It's okay if you do. It's not wrong, but nobody ever writes it. So we've used these now. Okay, so now we need to check the next part. Okay, so this is my next one up. And I only have this term left over here, and it doesn't match. So I'm just going to write this down. And that's used up. And now this guy's all by his lonesome. So it's minus 2ab. Right? And that would be our final answer. And you can just go through and double check and make sure that this variable combination does not show up in any of the other terms. And as long as you're good there, as long as each variable combination shows up once, you have simplified this completely. And that's the idea, right? Now, for multiplication, you have to be able to add polynomials because you end up collecting like terms at the end of these things most of the time. Um, excuse me. And you have to be able to multiply monomials. And we talked about that before. In fact, we multiplied a few monomials before. So let's go ahead and start taking a look at multiplication now. Okay, so if I'm multiplying monomials, right? These are the ones that look like, 5a squared b to the fourth times 3a to the third b squared, right? Those are two monomials. And we did this in the last thing. Basically, what we do is we handle everything. We do the numbers first, and then we handle each of the variables in kind. So 5 times 3 is 15. A squared times a to the third is a to the fifth. And then b to the fourth times b squared is b to the sixth. Right? And then we have our final answer. Every variable is represented one time, and all exponents are positive. And actually, you won't have to worry about negative exponents with polynomials, because if something has a negative exponent, it's not a polynomial. So it works out pretty well. Okay, so that's multiplying monomials. Now, if you're going to extend this a little bit, and let's say I have 5a squared b to the fourth, and I actually want to multiply that by 3a squared minus 2b. Well, here's my suggestion, just because I suspect a lot of you know how to do this already, but haven't had it called this. So what I want you to do is go ahead and pause here and see if you can take your best stab at what you think you should be doing with this. And then once you finish that, once you've exhausted your thoughts on that, play it again and see if you were right. Okay, so go ahead and pause it right here. All right. So let's go ahead and take a look here. So this is, what do you call it? This is basically an application of the distributive process, right? So I'm going to take whatever's outside here, it's going to multiply times that, and then multiply times that. So first off, I have to multiply these two guys. So 5 times 3 is 15. A squared times a squared is a to the fourth. And then b to the fourth is just b to the fourth. And then we have to multiply it times the second one. So 5 times negative 2 is negative 10. There's no a's to change this a squared, so we'll just write the a squared down. And then b to the fourth times b is b to the fifth. Right? And that's as far as we can go. I don't have any more like terms to combine, and each expression is simplified to the point where each variable shows up exactly one time in the term. So, and there's no negative exponents. So this is our final answer. Right? And notice it was just the distributive process. That's all it was. And honestly, all of polynomial multiplication is an application of the distributive process. Now, once we cross over the line here and start looking at binomials, like multiplying two binomials, there are multiple ways to do this. Now, most people are familiar with FOIL, and I have absolutely no problem with using FOIL. And then for those of you who don't know what this is, I'm going to explain it right now. And so what FOIL is an acronym that tells you an order, not the order, but an order that you can multiply things in that will give you a correct answer. There's more than one order. It's just this one happens to always work, so we use it. And it makes it a little bit easier to remember. So if I have something like x minus 3 times y plus 2, okay, and I want to multiply these two binomials. Excuse me. What I'm going to do is follow this order, right? We have FOIL, and that's our acronym. And I'll tell you what each one of these letters stands for now. This stands for first, outer, inner, and last. And so this just tells you how you can multiply these things. Let me show you how this works. So the first terms are x and y, right? It's the first term of each binomial, so you can multiply that first. That gives you xy. Then outer, so that's the outside terms between the two. So that's 2 times x, so that's plus 2x, right? Then the inner terms, which are these two, so it's minus 3y. And then the last terms, which is negative 3 times 2, which is negative 6. Right? And we have no like terms here, so there's nothing to collect. And this ends up being our final answer. We have 4 terms in our answer. Right? And that is one method. I have no problem with this method. The only problem is this only works with binomials. Right? If you're multiplying 2 binomials, FOIL's a good way to go. It's very efficient. It's very quick. One of the ways I like to multiply things, and I'll probably be doing quite a bit of this, is using the box method. Now, if you're not familiar with the box method, what's nice about it is that it works for polynomials of any size. So if you have 2 trinomials and you're multiplying them, box method works fine. In fact, it's not that much more work than just multiplying 2 binomials. So let's look at the box method. So this was FOIL, and that works for binomials. So the box method, and by the way, this method is called a lot of different things. Box method is what I've settled on, but I've heard it called a generic rectangle, a magic rectangle, a polynomial rectangle. I've heard lots of things. So this is how it works. And I'm going to work out the exact same problem. X minus 3 times y plus 2. What you do is you take one of the polynomials and write it across the side or across the top, right? And you separate each term with a line. And then you take the other polynomial and you write it across the side. Now, just as a notation thing, I like, if one of them has a subtraction and the other doesn't, I like to write the subtraction vertically so I can put the subtraction right here because it makes it harder to miss the negative, right? And then we divide these too by terms. Okay, once we have that, what we do is we just treat it like a multiplication table, and I'm going to multiply anything that shares a side. So we have xy here. For 2, the two sides of 2 are x and 2, right, for this box. So that's 2x. And then down here, I have negative 3 times y, so that's minus 3y. And then negative 3 times 2 is negative 6. And you'll notice they're the exact same terms I have over here, right? There's no difference. The biggest difference, well, I finished saying there's no difference, and then I point out the difference. There's no difference in the answer. What it does make a difference with, though, is if you make a mistake, it makes it a lot easier to track it backwards. Because once you have these terms here, you collect your like terms and write down your answer. We have no like terms, so our answer is xy plus 2x minus 3y minus 6. If I've made a mistake in here, one of these terms are wrong, I can go back and track it all the way to the beginning of the problem. Like if my 3y was wrong, okay, well, where did I get 3y? It came from over here. Well, what did I multiply to get minus 3y? I multiplied minus 3 and y, and that looks right. So maybe I wrote the problem down wrong, and you can go back, you can chase it all the way back to the original problem. So this is really good for bookkeeping because it makes it easier for you to find your mistakes if you make one. Right? That's one of the reasons I like it. The other thing is it makes it very mechanical. It makes it very clear that all you're doing to find these terms are multiplying 2 monomials. Right? So let's go ahead and take a look at another one here. So let's go ahead and clear that out. And as we go through these, I'm going to have you guys pause at each one of them and just give it a shot and see what happens. So let's multiply. Yeah. So we want to multiply here. Let's go ahead and see if we can do x minus 3 times z plus 4. Okay, so you can try that one out. And then also, let's do 2x minus 1 times x plus 3. Okay, so notice the one on the left has two variables. The one on the right only has one variable, and it's used twice. Okay, so see what you can do with that. Go ahead and pause and see if you can multiply out both of these and get the correct answer. Okay, so now being these are binomials, you can actually work it out either way. You could use FOIL or you can use the box. So I'm going to use the box on the first one here, and I'll use FOIL on the second one just so we can see everything. So let's see here. I have x minus 3 down the side and then z plus 4. And I just need to divide that up. So that gives me xz, 4x minus 3z and minus 12. And I'm looking through here. I don't see any like terms, so that means I can just write everybody down. So that's x times z plus 4x minus 3z minus 12. Not so bad, right? Okay, so let's look at this one here. I'm going to use FOIL on this one just so we can see that these work out in more than one way. So let's see, that's first. So 2x times x is 2x squared. Outside, let's see here. So that's 2x times 3, so that's plus 6x. And then inside, and then last. Now, here's something that's different. You notice the middle two terms are like terms. So we have multiplied it out at this point, but we haven't finished simplifying our answer. So if you enter this the way it is right now, you would actually get it wrong. The middle two terms on this, 6x and minus x, are like terms. So I can combine those two together. So 2x squared has no friends. And then that gives me plus 5x and minus 3. Right? And that ends up being our final answer. Now we have no more like terms to collect. Okay, so let's go ahead and try a couple more here. These are fun, right? I'm sorry, I didn't hear that. These are fun, right? Okay, well, I'll pretend I heard applause. Okay. So got a blue, yeah. So let's go ahead and try these two. And so let's see what we have with those two. So go ahead and pause here, see if you can work them out, and then we'll go ahead and work these out together. Okay, so I'm assuming you've paused and worked on this. So once again, I'm going to work these out both ways. So this first one here, I'm going to go ahead and work out using the box method. So let's see here. We have 2x plus 5 across the top and 3x minus 1 across the bottom. Oops. There we go. So let's go ahead and divide this guy up. Try that again. There we go. Actually, let's move that up a little bit. Okay, so 2x times 3x is going to give me 6x squared. 3x times 5 is 15x. And minus 2x and minus 5. So looking at this, notice, and this happens a lot with the box method, your like terms end up on diagonals from each other. So 6x squared doesn't have any like terms, so now I've used that one. Minus 2x plus 15x. You could write them down if you want and then collect the like terms if that's nicer, but I like to collect them right here. Minus 2x plus 15x is 13x. So now I've used these guys, and that leaves me with minus 5. Right? So that's not too bad. So I multiply two binomials, I end up with a trinomial. It's kind of fun. Go home, show your friends, all that kind of good stuff. Well, you're probably already at home, so. Anyways, let's go ahead and take a look at the second one now. So this one I'm going to go ahead and FOIL just because. So multiplying the first terms here, that gives me 9x squared. The outside terms, that gives me plus 15x. The inside terms gives me minus 15x, and then I have minus 25. Now, I need to go through and collect my like terms. Let's see here. 9x squared, there's no other x squareds. So that's it. But we do have two terms with x in it. But it's 15x minus 15x. And that leaves me with 0 x's. So there's nothing to write here. These guys just cancel out. And all I have left is minus 25. Right? It's kind of a peculiar little thing. And one of the things we're going to see later on, we're going to focus on it more, but I figured I'd point it out now, is you notice these two, the original two terms were the exact same terms, except the operation between them changed, right? One was minus and one was plus. And then our answer, you notice 9x squared is the square of the first term. If I square 3x, I get 9x squared. And the second term is the square of the second term, right? 5 squared is 25. So you're going to notice this pattern popping up. And it's not hyper important right now for you to notice it, but it will be later. So it's a good time to start seeing it. Even though we don't know what to do with it yet, it will save us time in the long run. And this pattern is actually important enough in math where it ends up getting a name. It's called the difference of squares. Because of the fact that this is a square and this is a square, and subtraction means I'm taking a difference. So it is a pattern, and we will be looking at it more in the next chapter than in this chapter, but we will definitely be using it quite a bit. It comes in quite handy. Okay, so let's go ahead and walk through the next one. Now, so let's go ahead and really stretch ourselves out a little bit here. Let's say I have 2x minus 1 times x squared plus 3x plus 1. And I want to multiply those two things. Now, this is not something you can use FOIL on, so you have to be able to expand the box to accommodate the extra terms. What I'd like you to do is see if I think you probably have a gut feel for how to do this that is probably correct. So go ahead and follow your gut feel and do what you think you should do with this. And then we'll work it out together and see if your guess was right. Okay, so go ahead and pause it here. All right, so let's take a look here. Now, if you don't like using the box, one of the things that you can do instead of FOIL is you take the first term and you multiply it by each one of these second terms. And then you move to the second term and you multiply it by each one of these terms, right? So basically everyone gets multiplied by everyone. The box takes care of that for us, right? So this is 2x minus 1. And you could write the short factor across the top if you want. You just have a longer box. I like to put my box horizontal. Right? So we just need to multiply these guys out now. It's not the neatest thing, but it will function, so that's good. All right, so let's see here. We have 2x times x squared. And let's switch colors. So that's 2x cubed. And then 2x times 3x, which is 6x squared. And then 2x times 1, which is 2x. And then down here, I have negative 1 times x squared, so that's negative x squared. And then negative 1 times 3x, so that's minus 3x. And then negative 1 times positive 1 is negative 1. And so now what we need to do is just go ahead and collect our like terms. So we got 2x cubed, and there's no other x cubes. I've always thought x cubed would be an excellent wrapper name if I was to switch from being a math teacher to being a rapper. I would go by x cubed or maybe Math Daddy or something. I don't know. Maybe Slope Dog. I always liked that one. Anyways, to continue here, 6x squared minus x squared is 5x squared. So now we've used these. Minus 3x plus 2x is minus x. So now we've used these, and then I have minus 1. Right? So I just multiplied a binomial by a trinomial, and I got a 4-term polynomial back. Right? And this is your final answer. And basically, everything just expands. Once you figure out the box, everything else you can just use the box for. If it's 2 trinomials, you can use the box. It actually doesn't even take that much more work than 2 binomials. It's just an extra row and an extra column. So let's go ahead and take a look at one of those. All right, so this is about as crazy as it gets, to be honest. And if you can handle this, you can handle anything that's going to be coming in this chapter or in this section. So let's say I have x squared minus 3x plus 1, and I'm going to multiply that by x cubed minus 2x plus 3. Okay, so we're going to multiply 2 trinomials this time. That's good, clean fun right there. But honestly, if you can get through this, you have this. You understand this completely. Okay, so pause it here, check, see if you understand it completely, and then go ahead and play it again and watch my solution. All right, so let's go ahead and take a look here. Now, honestly, I would not advise using anything except the box to multiply these. I find that when you multiply these by hand, it's very easy to lose track of your pieces. But if you use the box, everything stays in order. And that could just be my own chaoticness and my own disorganization, but it still helps. Okay, so we just need to fill in the boxes. And all that is just multiplying a bunch of monomials. So let's see here. So x cubed times x squared is x to the 5th. X cubed times minus 3x is minus 3x to the 4th. And then 1 times x cubed is x cubed. And then minus 2x times x squared is minus 2x cubed. Minus 2x times minus 3x is positive 6x squared. Minus 2x times 1 is minus 2x. Then, last row, 3 times x squared is 3x squared. 3 times minus 3x is minus 9x. And 3 times 1 is 3. So we have all our terms here. It's just a matter of collecting anything that might be like terms and going from there. Notice that the like terms aren't on the diagonals this time, right? If I look at the diagonals here, these aren't like terms. Some of them are, but in general, it's not. So you can't count on that, but most of the time it is like that. So let's go through these one at a time. So x to the 5th, he's by himself. X to the 4th, I only have one of these, so it's minus 3x to the 4th, and we've used that now. Now we have to collect our x cubes. So I have minus 2x cubed plus x cubed, so that's going to give me minus x cubed or minus 1x cubed, so we've used those now. And then we turn to the x squareds. So I have 3x squareds and 6x squareds, and that makes 9x squareds. So those are done now. And then I have the x's. Minus 9x and minus 2x makes minus 11x. Right, so let's see here. Let's check our exponents and make sure they're moving down as we move across to the right. We got 5, 4, 3, 2, 1. And so that means we're good. Nobody ever writes the 1, so you can leave it off. And this is our answer. If you got this answer, you have command of this, right? You can multiply. And that's the main thing you have to be able to do. Now, where we're going from here is we're going to be doing this process backwards. So you're going to be handed something, like this, and maybe not quite that complicated, but the idea is to figure out what got multiplied to give you this. And so really, the same way we're looking for prime factorizations of numbers, right? Like 6 is 2 times 3. Those are both prime numbers, so that's the prime factorization. We will be looking for prime factorizations of polynomials, and that's a little more complicated process. So we end up spending an entire chapter on doing that. And that will, and then once we have that process down, we'll be able to put these things in equations and work with them from there. But nonetheless, if you can handle anything we did here, you should be fine through the homework and the quiz. So until next time, keep your pencils and your wits sharp.